Welcome back to this course on multi-core systems. In this lesson I will present two optimizations to the baseline full directory protocol. The first optimization reduces the latency of coherence transactions. The second optimization reduces the memory overhead of the full directory protocol. There are several optimizations that can and have been applied to this basic presence flag factor or full directory protocol. The first optimization is to send the missing block directly to the local node instead of via the home node. This is in fact a variation of the baseline protocol implemented in the Dash multiprocessor, which was developed in the late 1980s by a group led by Anup Gupta, John Hennessy, exactly the author of the textbook, and others. Dash, by the way, is the acronym of Directory Architecture for Shared Memory, and this multiprocessor had a lot of influence on other multiprocessor designs. To give you an example optimization, this is what we did when we had a read miss to a block dirty in a remote node. First the local node sends a read miss to the home node, then the home node forwards the read miss to the remote node. After that the remote node replies the block to the home node, and finally the home node forwards the reply to the local node. So overall the latency is at least 4 network traversals. In the Stanford Dash protocol, this is reduced to 3 network traversals as follows. The first phase is the same. The local node sends a read-miss message to the home node. The second phase is also the same. The home node, upon receiving the read-miss message, the home node discovers that it is dirty at a remote node R and forwards a remote read message to R. The third phase is different. Instead of sending the reply message first to the home node and from there to the local node, the remote node sends the reply directly to the local node and simultaneously to the home node. These two messages can be routed independently and simultaneously through the network, and so the latency of the read miss has been reduced from 4 to 3 network traversals. This is just an example optimization. I can give more examples, but discussing them is beyond the scope of this course. If you'd like to know more, watch my other specialization on multi-core systems. Finally, a few words about the memory overhead of the full directory protocol. Obviously, it increases linearly with the number of cores, since for every core a presence flag bit has to be maintained. Furthermore, it also increases, not relatively but absolutely, with the size of the highest shared memory level, which can be a shared cache or main memory. Let's consider 2 examples. For the first example, suppose the block size is 64 bytes and that there are 8 cores. Then we need 8 bits for every directory entry, 8 presence flags and 1 dirty bit. So the relative memory overhead is 9 divided by the number of data bits, 64 times 8, which equals 1.8%. This might be considered negligible, even though there is no such thing as negligible in computer architecture. For the second example, suppose the block size is again 64 bytes, but now there are 64 cores. Then we need 65 bits for every directory entry, and the relative memory overhead is 12.7%. This is significant, even in modern times when there are billions of transistors on a chip. Also for this problem, several solutions have been proposed and implemented. The first solution is based on the observation that few blocks are actually shared between nodes. In other words, if we have a multi-core with, say, 128 cores, it is very uncommon that all of these 128 cores have a copy of the same block. It is far more common that at most, say, 4 cores have a copy. The solution based on this observation is called the Limited Pointer Directory Protocol, or DARE-I protocol. It maintains a factor of pointers to nodes that have a copy of the block rather than a single bit for every node. The biggest problem of this protocol is, what do we do when we run out of pointers? In other words, when there are more sharers than the maximum number of sharers indicated by the factor length. The second solution is based on the observation that while there are many memory blocks, at any time relatively few of them will be cached, since the cache size is much smaller than the memory size. The solution based on this observation links the cache copies in a linked list. For example, if a block is cached in nodes 1, 3 and 7, then the copy in the cache of node 1 indicates that the next sharer is node 3, and the copy in the cache of node 3 indicates that the next sharer is node 7. Very roughly, this describes the scalable coherent interface protocol, which is in fact an IEEE standard. One problem of this protocol is, however, that it increases the latency of writes, since invalidation messages can no longer be sent simultaneously to all sharers, but must follow the linked list. Again, I do not have the time to describe these as well as other solutions in detail. You know where to watch to learn more. Finally, an exercise to test if you understood the memory overhead of the full directory protocol. Suppose we have a cache-coherent non-uniform memory access CC/NUMA architecture with 128 cores and cache blocks of 32 bytes. What is the relative memory overhead of the full directory protocol? With the information and examples I gave you on the previous slides, you should be able to perform this exercise. Thanks for watching this video. In the next lesson, I will discuss the synchronization problem and describe some special instructions needed to synchronize in shared memory systems. Hope to see you back.